Hello, my name is Leslie Vittling, and today I'm going to talk to you about Juno at Jupiter with a focus on its extended mission and what my role is with the spacecraft. Next slide. A little bit of background. I got my bachelor's in geology from Purdue University and my master's in planetary volcanology at the University at Buffalo with Dr. Tracy Gregg. There, I looked at fractal dimensions of lava flow margins on both Mars and Earth. I then jumped from the science side of things to the operation side of things, and I've spent the last 17 and a half years at Malin Space Science Systems in San Diego, working camera operations. I've spent the last decade on Mars, working on MGS, MRO, and MSL. Then in 2015, I got the opportunity to jump to Jupiter, and I haven't looked back since. I am now a senior research associate at PSI, working on the Juno mission with Candy Hansen. Next slide. So what do I do on Juno? I am the operations lead for JunoCam, which is the visual camera aboard Juno. My main responsibility is planning and commanding of imaging sequences for each Jupiter flyby. Now this is about 125 to 200 imaging commands per sequence. I'm also responsible for the health and safety of the camera, and I monitor this daily through telemetry. Any images that come down from the spacecraft, I log, map project, and push to the public website. And then I finally end up archiving all these images with the planetary data system. Next slide. Now I want to focus on Juno's extended mission trajectory, but first I'd like to review the primary mission trajectory because it's actually important to understand and where we ended up in the extended mission. So the original plan was two 53-day capture orbits, followed by a significant burn called the PRM, or period reduction maneuver. And that was going to burn us from 53 days down to 14 days. Now, what ultimately happened is that we had the two 53-day capture orbits, but just before the PRM, or the burn, was to execute, there was a fault reading with the main engine check valve. An analysis determined there was actually a risk of main engine failure if the burn was to proceed. So the project did not want to accept this risk and instead let the spacecraft in 53-day orbits. And that's what this diagram is showing you. The top diagram is the original trajectory. The bottom diagram is what we ended up flying. Now, as you can imagine, a plan with 14-day orbits is going to be a lot quicker than what it will take if you leave the spacecraft in 53-day orbits. So the original plan was a 20-month mission. What ultimately happened is it took 5 years to accomplish the prime mission. While no PRM, or the burn, was a disappointment, and some even considered it a failure, it actually provided a brilliant insight into planning creative trajectories. So what am I talking about? Next slide, please. This is what the extended mission trajectory ends up looking like. Let's start in the upper right-hand corner. This is an orbit plane projection of Juno's mission. Jupiter is in the far, far right-hand corner while all the orbits overlap. Now the prime mission is in gray, and the extended mission is in the colors, the turquoise, the blue, and the purple. Now remember, primary mission is 53-day orbits, where the extended mission has different orbit periods. So extended mission phase 1 is actually a 43-day orbit. Extended mission phase 2 in the blue color is a 38-day orbit, and extended mission phase 3 is a 33-day orbit. So what's governing this change in the orbit period? Well, it's actually the gravity effect of flying past Jupiter's satellites at such close distances. So let's look at this bottom graphic. This is a meridian plane projection of Juno's mission. Now, Juno always flies in over the North Pole and out the South Pole. The gray, again, is the prime mission. Now, just before Perigove 34, we did a small maneuver with our thrusters, and we flew very close to the surface of Ganymede. Now, if you missed this, I've included images of this later on in this presentation. But flying as close as we did to Ganymede its gravity effect actually changed the orbit period from 53 days to 43 days. Now, we just finished Perigeo 35, so we're in the very early stages of extended mission, so we will remain in 43-day orbits till just before Perigeo 45. There we will fly very close to the surface of Europa, and its gravity effect is going to change our orbit period from 43 days down to 38 days. We will remain in that 38-day period until Perigeo 57, when we'll fly very close to the surface of Io, and its gravity effect is going to change the orbit period from 38 days to 33 days. Then we will stay in that 33-day orbit until the end of mission, which is Perigeo 76, and that's September of 2025. Now, the graphic in the upper left-hand corner is actually a top-down view. Jupiter is in the middle, and we're looking down on its north pole. And this just shows the progression of Juno's orbits through the mission. Again, primary mission is in gray. We start over around 270 degrees, and that walks to about 45 degrees where extended mission takes over. And you can see the length of the orbit petals is smaller and smaller, indicative of that orbit changes. Now, one lesson learned from Juno's primary mission is that science objectives can still be met and new discoveries can even be made, even if the orbit trajectory isn't exactly straightforward or goes as planned. So what happened in the primary mission with the no PRM, the no burn, ultimately led to some really creative thinking about how to plan Juno's extended mission trajectory. Next slide, please. So what are JunoCam's objectives in the extended mission? First and foremost, JunoCam is a public outreach camera and will remain so in the extended mission. The submissions that we have received from our citizen scientists on the science side of things, as well as the general public on the artistic side of things, have been absolutely stunning, brilliant, incredible, and so creative. These images on the left-hand side are a group of some of my more favorite artistic impressions that we've received. Probably my absolute favorite is the one in the upper right-hand corner. That's actually a quilt. This gal, Anne Harwell, takes our images and she sews the most amazing quilts out of them. Just goes to show that the public is still very engaged with our camera and is so incredibly creative. Another objective is monitoring the atmospheric dynamics, particularly at the North and the South Pole. Now, if you remember, before Juno, we never had imaged either the North or South Pole of Jupiter. When we first flew over in 2016, we got our first glimpse of these cyclone-like structures at the pole. Now, JunoCam cannot image the entire planet at once, and instead images little parts. So this citizen scientist submission on the right-hand side is actually a composite image of 4 different flybys. And what it's showing you is what we have termed circumpolar cyclones of the North Pole. Now, we started imaging in 2016. We will continue imaging hopefully until 2025. So it's almost a decade-long record of monitoring these atmospheric dynamics of these circumpolar cyclones. And finally, a third objective for JunoCam are the satellite encounters. Now, as I just stepped through in my prior slide, the satellites are completely dictating the entire extended mission trajectory, and it's namely Ganymede, Europa, and Io, and with good cause. Next slide. In case you missed it, we just flew by Ganymede this past June and acquired this absolutely stunning image on the right-hand side. This is at about 1,000 kilometers. Now, for comparison, on the left-hand side, I've included the image that JunoCam took at its closest approach in the primary mission, almost at 98,000 kilometers. Now, mind you, imaging the satellites in the primary mission was never a focus, but it truly is in the extended mission. Next slide. Here are some more incredible examples of citizen scientist contributions of our flyby of Ganymede prior to Perigeo 34. That middle image is actually a composite of 3 different JunoCam images. Now, if you think these images are truly stunning, you just wait. Next slide. In September of 2022, we are going to fly by Europa at a mere 320 kilometers above its surface. In December of 2023 and February of 2024, we are going to fly by Io at roughly 1,500 kilometers above its surface. So these two images that I've included on the left-hand side, being JunoCam's images that it's taken during the primary mission, are going to vastly improve. And we cannot wait to start planning this, and we are so super excited to see how these images turn out. Next slide. So now that Juno is in its extended mission, what will it discover next? This is such an exciting time, and I am so thrilled and so incredibly grateful that I have the opportunity to continue working on this mission and this camera at the Planetary Science Institute. Thank you.